Hi everyone, welcome to this lab 8 introduction video. In this lab, we are going to do systolic array on FPGAs. Systolic array is a dedicated structure for calculating the matrix multiplication here. It is widely used in applications such as neural networks, right? Where there's a lot of matrix multiplication or convolution operations. Okay, so in this lab, we're gonna do two different design of the systolic array. The first one is a 3D combination only design here, and the second one is a 2D design here. And for the pre-lab, you are required to do the simulation of the first design, and in your lab session, you are required to do the second design on the simulation and also on the board. Okay, let's get started with the first one. So yeah, so imagine we want to have a 2x2 matrix multiplication, which is A times B. So for A and B, we have 4 entries of them. So here we have, as you can see in this figure, there is A11, A21, A12, A22. Same for the B matrix here. We have 4 entries of the B. And the result of A times B will be saved in matrix C here. As you can see, we have a C11, C12, C21, C22 here, right? And so this is wire connection of this systolic array design, and for each of the node on these corners, this is actually a systolic array unit. This is a calculation unit. Okay, so this unit, the design of this unit is provided to you, and you will need to understand how this works and just create, let me see, you should create like, yeah, we have 8 instantiation of this unit, small unit, and we just need to connect the input and output properly with each other, of course with the input and output, and so that you will see the output at C here, right? Let me briefly introduce the systolic array unit 1 here. This is for the first time. Okay, so this is 1. Here, yeah. So we have 3 input, multiplication input 1 and 2, and we have the A input. This is the accumulation input. So when we do the matrix multiplication, so most of the operation are either multiplication or summation, but here we call summation as accumulation because we have to do the summation iteratively with the previous result here. Okay, and we have the multiplication input, the accumulation input, and the output is just the accumulated output. This out is summation of the accumulation input with the multiplication input of the multiplier. So the input of the multiplier is just mi1 and mi2 here. All right. So the equation is listed here. Out equals ai plus mi1 times mi2, and also we have 2 other output here. So we just directly assign mi1 to out mi1 and mi2 to out mi2. Why do we need this? You may ask. The reason is you can find the reason in this structure. Okay, so for example, for this node, we have A11 times B11, and also we have the initialized accumulation input as 0 here, right? So the result of A11 times B11 will be goes upwards to this node, all right? And this will be the accumulation input of this node. And also for the node here and the node here, they also need the value of A11 and the B11. And we don't directly create another wire from the input port to the other node. The alternative way is this input will pass through this node and then go through the output MI1 following this wire and then fit into this node here. And same for B11 here, right? B11 is coming in this node through the MI2 port here, and actually it will directly be assigned to out MI2 through this wire and get input into this node here. So B11 will be used in this calculation once, and then B11 will be used in this calculation the second time, right? Yeah, so basically it's because we need many data being used more than one times. This is why we need to pass these input to their neighbor nodes here and here. And same for let me see, same for example B21 here. It's going to be used in this node and also be passed to this node here, right? So the orientation of these input and output wires are matching with this figure. Okay, so the accumulation input comes from the bottom. MI1 and MI2 comes from the left, or this, or either this I direction or this J direction. Okay, so let me see. What you need to do for this part is here. You need to work on your code for this part. So we have already created 8 instances of this unit here, and the input and output are assigned to those wires, right? Let me see if I can zoom in. Yeah, okay, this is better. So we have these wires. These are 2D wires, right? So the first dimension is just a data width here. It's the size. Size is the parameter passed in from outside. And by default, it's 8, right? And also, we have a second dimension with degree of 8 here. So in total, we have 8 wires of unit MI1, and we have 8 wires for the second input. We have 8 wires for the accumulation input. These are assigned to the 8 instances of this small unit. So basically, those 24 wires, input wires for these 8 nodes here. Okay. Sure, and we also have the outputs here, right? So what you need to do is just to assign those wires properly, and either you do an internal connection here, 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 or you connect these wires to the input port and the output port. Okay, that will be it. And any behavior associated with the clock edges is already written here. So we just have to reset, and or each positive edges, we assign these MO wires to the MO register here, right? So you just need to do your combinational only connections here, Okay, combinational logic only, nothing sequential anymore for this first part. Okay, and let me see the menu. I think you need to do a test bench with, yeah. So you will have a test bench here, all right? We already provided two input for you. This should be these two matrix multiplication here, and you need to verify the result in the simulation. Okay, so that is all for the first part. We can move on to the next one. Let me see. Yeah, this is the next one. Um, so for the next one, instead of using this 3D architecture, here we have a 2D architecture. This is a more friendly um, in terms of the hardware design because all the chip we are dealing with, the FPGA chip, they are actually 2D chips, right? You have the X coordinate and Y coordinate, but you have only one layer. It's a 2D. It's a 2D structure. Oh, there should be two, by the way. Yeah, and another second difference is, as you can see, for the same 2x2 matrix, we have 8 small unit here, but we only need 4 unit here. So each square box is a systolic array unit for the second design. Okay, and also this is no longer a combinational logic design, but this also involves some sequential logic. So as you can see, for this whole design, still we need to do the 2x2 matrix A times B. So they share the same test bench actually. But as you can see, for the first design, we have 4 input for A matrix and 4 input for B matrix here, and 4 input for all zeros for the initialized accumulation values is 0. Okay, so in total we have how many? 12 inputs, right? But here we only have 2 input for A and 2 input for B. This is a critical difference because since we have 4 entries, right? But we only have 4 entries for each matrix, but we only have 2 input ports. So now the timing matters. Okay, so we need to be careful about the timing so that the 4 entries of the A matrix can be fed in their corresponding cycle, so that and also the B entries of the B should be fed in at the correct timing as well, so that we want to do the multiplication as a result as we want, right? Let's first introduce this small unit design. The small unit design, let me see. Basically, they are the same. We just have the multiplication 1 times multiplication input 2, and also plus the output here. Oh, this is the one difference. Okay, so previously we have the multiplication result plus the accumulation input here, and get the summation to the output here. But here we don't have the accumulation input anymore, but we just plus the multiplication result with the previous internal register within this unit. All right. So it is this is actually the accumulation here. Let me see. We should have an internal register here. Should be out. Yeah. So this is yeah, this is a register as you can see. So initially they are 0, and for each input of the multiplication input, we just accumulate the multiplication input to this register, and get it output. All right. Yeah. So this is a difference you may want to know. And for the same, we will also pass those multiplication input to its neighbors. For example, we have one entry of A here. We want to use its value in this node, and also we want to use it in this node here. All right. Yeah, and those pay attention to these. Okay, so in Verilog, these are non-blocking assignment here. So which means it's updated on each clock cycle. But for the previous one, as you can see here, so the input, so the change on the input will immediately be affected as on the output here. Okay, so this is why I said this is a combinational logic, but here there's a sequential one. All right. Let me see what else. Right. So yeah. So the unit has been introduced, and so we need to remember I said we need to take care about the timing here, right? So I have listed a timing for you here. Of course, I guess this is not the only solution, but I I can guarantee that this should give you what you want. Okay, so if you follow this schedule, um, you should be able to get um, the result as A times B, the matrix A times B here, right? Of course, I would recommend to just uh, handwritten this scheduling and actually know why we have this. For example, for the reset, we have all zeros internally reset here. So D here means we have registers here, right? Um, let me see. So for the first count, we have shift in the A11 and the B11 here, all right? And also for the so we can have the A11 times the B11 then. And for the second count, we have shift in A11. We have shift in 4 values. Okay, so remember in total we have 4 ports, right? So at the maximum read, we can shift in 4 values. So for here, you may ask, what is input for the other two ports? Here you just assign zeros. Okay. And then lastly, we assign A22 and B22. So you will know that the whole result will be ready until the fourth clock cycle here. Yeah, I guess this will be it. So yeah, so on Tuesday you will do this part in lab. You will also want to verify your implementation of this second systolic array with the same test bench. Also, you can verify by this equation, all right? And once you finish this, you will run it on the board with this testing program. Of course, this is just binaries. You can tell what is going on here. But in the testing program, you just do some other matrix multiplication. Maybe you will do 3 matrix multiplications, and it will show the result here, the result in the terminal, and you just verify it. And if it's correct, take a screenshot, include in your report. That would be it. Okay. I guess this is a relatively easier design compared to the previous ones. So I hope you can all finish them in your lab session, and good luck. Okay, thank you.